In this section, we want to take a look at the conservative vector fields and some of the ramifications of having a conservative vector field. Recall that in 2 dimensions, we find the gradient vector simply by doing the partial with respect to x and the partial with respect to y and putting them in a vector form. For example, if we've got the function y ln x plus xy squared, the gradient vector for that function would be the partial with respect to x, the partial with respect to y, written as a single vector. So this vector field, which we just created from doing the partial of x and the partial of y, is referred to as a conservative vector field. So this is what a conservative vector field is. It simply means that the components result from doing the partial derivatives, respectively, in 2 dimensions of x and y. So this is what we mean by a conservative vector field. So for computational purposes, we're going to take our vector field and refer to the first component as capital M and the second component as capital N. And we know that the partial derivative of x is the first component and the partial derivative of y is the second component. So if we take a look at this vector field, if it's conservative, then the first component is the derivative of some function with respect to x. Well, we can recover that function somewhat if we integrate with respect to x. So the integral with respect to x would be x squared y squared over 2 with some other constant. We'll talk about that later. However, there's an x squared y squared over 2. And if we integrate the second component with respect to y, we can recover the y value. The partial of y was x squared y, so the integral of that would be ax squared y squared over 2. Well, since those are the same, then the function that generated this vector field would be x squared plus y squared over 2. So that would be a conservative vector field. Now, since the first component was the derivative with respect to x, and the second component was the derivative with respect to y, if we take those and do the derivative of m with respect to y, that would give us the second partial fxy, which we call the mixed partial. If we do the derivative of the n component with respect to x, we get the mixed partial fyx, and we know from earlier that the mixed partials have to be equal. So this is our test for a conservative vector field. Does the partial derivative of the first component with respect to y equal the partial derivative of the second component with respect to x? So to test this vector field to see if it's conservative, we take the first component and the second component. We do the derivative of the first component with respect to y. We do the derivative of the second one with respect to x. And if these are equal, then this is conservative. Now there's a little more work to do if it's 3-dimensional. we have to find out if that is true for each pair. Now look at the pattern that develops. The first component was the derivative with respect to x. The second component was the derivative with respect to y. So the second derivatives that we're testing, in this case, we would want to know, is the derivative of m with respect to y equal to the derivative of n with respect to x. Now we got to take these two pairs. The first component, m, was the derivative with respect to x if it's conservative. The third component was the derivative with respect to z if it's conservative. And so we would need to check the second derivatives of those, which in this case would be the derivative of m with respect to z and the derivative of p with respect to x. Finally, the only other way of pairing up the three functions would be n and p. We need to check n's derivative with respect to z and p's derivative with respect to y. Now, for this to be conservative, all three of those have to be equal. For example, if we have this vector field, if we take the m, n, and p and do some checking, the derivative of n with respect to z and the derivative of p with respect to y are the same. So we go on to check some others. The derivative of m with respect to y and n with respect to x are not the same. So we don't need to go any further. This is not conservative. Checking this, we'll take the derivative of m with respect to y, the derivative of n with respect to x. Since they're the same, we'll pair up two more, m and p, m with respect to z and p with respect to x. And they're the same, so we'll check the last pair. So that is conservative. Now, if we have a conservative vector field, one of the things we're interested in is the function that would have generated the vector field. We call this the potential function, and we abbreviate that with the phi. Now, earlier in the video, we created a vector field from the function y ln x plus xy squared by doing the partial with respect to x and the partial with respect to y and writing them in a vector field. Well, that means that the y ln x plus xy squared is the potential function for that vector field. So let's see how to find the potential function for this vector field. Well, we know that the first component was the derivative with respect to x. So to recover some of our potential function, we can integrate that with respect to x. That gives us the function x squared y plus some constant of integration, which in this case can be some function of y. We'll do the same thing with the second component. If we integrate the second component with respect to y, we can recover some of our potential function. But again, there's some of it that we can't recover. Now, combining these two together, you see that we definitely have an x squared y in both of them. So our potential function has to contain an x squared y. Now, in the first integral, we had some function of y as our integrating constant. And sure enough, here is the function of y that's specified in the other one. And so there's our potential function. This is just going to be some constant. There's no more x's involved, or they would have come out in our integral in step 1. Now similarly, if we have three-dimensional vector field, we take the first component and integrate with respect to x. Now the integrating constant is some function of y and z. We integrate the second component with respect to y, and again the constant is some function of x and z. And we integrate the third component with respect to z. We combine these together. You can see that we've got an x squared y squared, which must be the function of x and y alluded to in the third integral. We also have a yz squared, which obviously is the function of y and z alluded to in the first integral. And we've got some other function of x and z, which, as you can see in the other integrals, there are no more functions of x and z. So that becomes our constant. Now, oftentimes in physics and engineering, we're asked to compute the work done by a force field on an object. And so that would be nothing more than the line integral of f dot dr. Now, what we're focusing on now is, of course, what happens if it's a conservative vector field. So, if we want to find the work done by this conservative vector field, when we go from the point 0, 0 to 1, 1, between these 2 points. So if we go along the path directly from 0, 0 to 1, 1, the straight line, this would be the parameterization for that line. And we'll do f in terms of t, do the r prime, f dot r prime, and do the integral. Now if we want to go along the path x equals y squared, we do the same thing. We parameterize, do the changeover of f from x's and y's to t's, do r prime, do the dot product of those, and then integrate. Same value. Here's along the path y equals x cubed, and same thing, we parameterize, do the changeover of f, x's and y's to t's, r prime, dot product, and integrate. Notice we get the same thing. We mentioned this earlier. So what do you think are the conditions under which we would get the same answer regardless of the path? That would be if it is conservative. So only when we have a conservative vector field do we get the same line integral regardless of the path. Hence the term conservative. Now, the interesting thing is that we have this leading us to another important idea, and that is the only thing we need to evaluate the line integral in a conservative vector field are the endpoints. Now, I'm going to show you a little bit more about this, but notice the conservative vector field given here, we just did this, has the potential function x squared y over 4. Now we can evaluate the line integral by simply substituting the endpoints into the potential function. Now, since this is a lot like what we learned back in Calculus 1, which we called the fundamental theorem of calculus, which says you can do the integral and substitute the end point minus the beginning point and subtract to do the definite integral, we do a similar process, and this is the fundamental theorem of line integrals. And this is basically the idea behind the fundamental theorem of line integrals. Now here's just a little rationalization for the fundamental theorem. We can write df dt by using the chain rule as df dx times dx dt, df dy times dy dt added together, which we can modify by writing it in vector form and recognizing the two vectors, grad f and r prime. Now, since this is df dt, we can do the integral of that by integrating df dt. Well, that would be the same as the fundamental theorem of calculus with a little revision, and that's the capital A means the point where t is equal to A, and capital B is the point where t is equal to B. Now, I'll show you how to use the fundamental theorem of line integrals on a specific example here. So if we take this vector field and check it, we find that it is conservative. So we can apply the fundamental theorem of line integrals, which says we can find the potential function by integrating the first component with respect to x and the second component with respect to y, and then reconciling those two. So that would be our potential function. We could substitute in values into the potential function. We can evaluate the line integral of this vector field from 0, 0 to 1, 1, regardless of the path, by plugging in the 1, 1, the end point, and the 0, 0, the beginning point, into the potential function. So we're given the vector field x comma negative y, and we're told here is its potential function. We can evaluate the line integral of the vector field from the point 1, 0 to 0, 1 along the quarter circle simply by taking the point 0, 1, plugging it into the potential function, and the point 1, 0 and plugging it into the potential function and subtracting. Now the same thing works in 3 dimensions. Now if we take this vector field to evaluate the line integral of this vector field, it would be nice if this was a conservative vector field. So let's test it out by looking at the partials. So it is a conservative vector field. Well, let's find its potential function. So integrating the first component with respect to x, integrating the second component with respect to y, and the third component with respect to z, and then reconciling those, we find our potential function. We can take the potential function, substitute the point 1, 2, 3, substitute the point -3, -2, -1, and subtract. Now, one last observation concerning conservative vector fields, and that is, what if we have a closed curve? Well, you can probably figure this one out yourself. If your curve begins and ends at the same point, and the fundamental theorem of line integrals says you substitute the endpoints and subtract, then you'll be subtracting the same two values. Now here's a problem that we actually had in an earlier section. We have this vector field and we check to see if it's conservative. Well, if it is conservative, then our work is finished, because the line integral of a closed curve on a conservative vector field is 0.